So, a lot of times the oxidative phosphorylation and photosynthesis are compared and contrasted. Okay, what the purpose is between the two processes is the fact that electrons are moving and we're going to create energy. And so what we're going to see is the electrons moved in oxidative phosphorylation because we totally just broke down our foodstuffs and made electrons flow. In photosynthesis, we're going to do it differently, and we're going to use the sun to make electrons flow, but what we're going to do is we're going to create energy molecules. Then we're going to take in photosynthesis one step further, and we're going to use those molecules to make sugar. And so photosynthesis has two main steps, one that are called the light reactions, ones that are called the dark reactions, and we're going to go be both on the dark side and the light side of the force here. So what's going to happen is light is going to shine, and we're going to start with water, and the waste product is going to be oxygen. Now, that's kind of a little bit different than what we saw in oxidative phosphorylation, right? The waste product was what? Was water, and we used oxygen as the reactant. So it's totally opposite. And what we're going to do is we're going to build two energy molecules, NADPH and ATP. Now, ATP you know, right? ATP has energy because of the bonds. ATP has energy really in the phosphates and the negative charge that is very compact together. NADPH is very close to a molecule that we've seen before. What was the molecule that we saw before that looked like NADPH? NADH. That was an electron carrier, right? And NADH accepted a hydride. And so in the process for the glycolysis and citric acid cycle, we accepted hydrides and carried them. Here in NADPH's case, what's going to happen is the physiological use of NADPH is to donate a hydride. All right? And it's a reductive molecule, whereas the NAD plus becoming NADH, it's an oxidative process. And so, but remember, when I made NADH, I called it a pool of energy. The NADPH is going to be a pool of energy also. And then we'll use both the ATP and the NADPH to take in CO2 and create sugars. All right, and in the compare-contrast, we took sugars in by eating glucose, and we created CO2 at the end of the process as the waste product. And so both of the reactants here are the waste products from us, and both of the things that are coming out as the products here are the reactants that we use in our process. And so it's kind of the circle of life right here in one fell swoop: photosynthesis and then glycolysis all the way through oxidative phosphorylation. Now, where this occurs is in plants, in particular green plants, and in the organelles called chloroplasts, and we will take a look at what is happening in the proteins that are there. Oh, this is also wonderful. Check out that nice, simple reaction. It looks so nice. It looks so simple. It is so complex in terms of getting it all done. The thylakoid membrane is very much like the mitochondria in that there's a lot of membrane space, okay? And so there are a lot of proteins that are embedded in membranes, and electrons are going to flow, and so there's a lot of parallels. Now, as the electrons flowed through the electron transport chain, what was the result of that? As the electrons, all the electrons moved through all the different complexes, what was the end product of that? Where was the energy? in the proton gradient. What do you think is going to happen when all of these electrons run through? What are we going to build? A proton gradient. Okay? And so we're going to be very similar in that we're going to change where protons are and make a proton gradient so that we can make ATP. All right? Now, one of the products that is also going to be made is the direct movement of those electrons is going to be in the NADPH, and so we'll make another power source there. Now, there's a lot of things that are happening in photosynthesis, and what we're going to do is we're going to need things that absorb energy from the sun. And so we will talk about chlorophyll, and we'll talk about its actual structure in just a moment. Now, what's going to happen is the light is going to come down, and we're going to get excited. Remember ground state, excited state? What is an excited state? I'm excited. What happened? Yeah, it's a higher energy. What is moved to make it higher? An electron. We're actually going to make an electron go from a ground state to an excited state. Now, that's all well and good, and we've done that in GChem. We talked about excited states, okay? But usually that means one electron jumps from one level to the next, right? And it can jump several levels, but it's all within a protein. It's all within an atom itself, and then it falls back down, and energy can be given off. But in this case, we're going to give it so much energy, and we're going to have the right symmetry and arrangement of things. The electron is not going to just jump up in energy, but it's also going to jump up and then move from one place to another. I'm going to create separate charges. Have you gotten to separated charges in physics yet? If you separate a charge, it's called a capacitor, and it's a measure of energy. And so we're going to have these electrons being moved. They will separate in charge. It is going to be governed by the fact that we're going to have twofold symmetry in what are called reaction centers. And as all of the electrons flow from one place to another, we will generate a proton gradient. Now, one of the products that is the waste product is oxygen, which is very important for us, right? Plants don't need oxygen. They use oxygen, or they give off oxygen. And we thought, okay, is that actually necessary? Well, it really isn't, because there are a lot of plants that grow and don't produce oxygen if that isn't necessarily what is available. If water is not available, the plants can actually use hydrogen sulfide. Why is hydrogen sulfide acceptable? If you take a look at water and hydrogen sulfide, or oxygen and sulfur, how are they related? Take a they're in the same group, right? They do the same kind of reactions. And so what happens is, if you actually give it hydrogen sulfide rather than water, you can create a sugar, but what the outcome is pure sulfur. The elemental sulfur comes out instead of the elemental oxygen. All is really needed is a place for electrons to be accepted, okay? And so I'm going to accept electrons in the oxygen or accept electrons in the sulfur, and we can move things around. So it's a redox problem. It really doesn't matter what is the component. I don't even need CO2. I can actually use metals, and I don't have to make sugar. All I have to do is have electrons flow from one entity to another, one that can accept electrons, one that can give electrons, and I can make this process run. The enzymes can do that. Just so happens that the fact that it does make sugars and produce oxygen, which is very beneficial to us, is important in the balance of life. All right, so what's really important here? Well, we're going to extract all this energy from light. We need to actually absorb that light. So we need what is called a chromophore. Okay, what is a characteristic of an organic molecule that absorbs light? What does the organic structure have to look like to absorb light? Conjugated double bonds. Okay, an organic molecule that absorbs light is called a chromophore. Okay, the species chlorophyll is one of those that does it. Here is the structure of chlorophyll. Looks just like the ring structure of heme, and in terms of hemoglobin, but the metal is different. It is magnesium rather than iron. Okay, there are two versions. Chlorophyll A is what's drawn, and then right at the top here is if you exchange this organic structure for that methyl, you'll get chlorophyll B. All right, and then there's some chlorophyll in bacteria. So the chlorophyll structure, you can see conjugated double bonds. It is hydrophobic, and it can absorb electricity, or not the electricity, it can absorb the energy of a photon. And it actually absorbs 1 photon of light, and within this structure, it will excite the electrons in the metal magnesium, and it will make them into the excited state, which is wonderful, what we need to have happen. Now, if you take a look at the absorption between chlorophyll A and chlorophyll B, you can see two differences. Okay? What do you see as the difference between them? Yeah, they absorb at a different wavelength. Not too different, do they? They're almost on top of each other, the absorptions. Why in the world would they be so close, or why in the world are they actually even different? Why are they different? Changed what? Has an oxygen, yes. Not just an oxygen. What is CHO in organic? If I write, it's a what? An aldehyde. And it's an aldehyde that is right in conjugation with all those other double bonds. Putting one more aldehyde in the mix changes how many conjugated double bonds, which changes the maximum absorbance. Any single double bond will absorb radiation, but in what wavelength? A single double bond will absorb light. It doesn't absorb in the light spectrum. It absorbs in the UV range. You put 2 double bonds that are conjugated, still in the UV range. 3, still in the UV range. 4, 5, or 6, you start moving into the area where you're absorbing in the visible light range. The more you have, the deeper you get into the absorption spectrum, or the wavelengths within the light. And so we have chlorophyll that absorbs in 2 main areas. Now, the wavelengths from 400 to 700 represent most of the energy that's coming off the sun. Are we absorbing every single energy that the sun puts out with chlorophyll? No. But it just so happens that God has designed lots of different chromophores that will absorb at different wavelengths maximally. Some of those are there. Both chlorophyll A and B are in that range. You can see the intensity line at the top, where the amount of those energies at those different values, which represent just different wavelengths, the colors do. And so there are a lot of different organic molecules that can absorb light. If you take a look at what are called accessory pigments, have you ever heard of this? Beta carotene? Where do you get that from? Carrots. Eat lots and lots of carrots. Beta carotene, if you cut it in half, creates the absorption molecule, the chromophore for the rods and cones of your eyes. And so all of these others are large organic molecules that have lots and lots of double bonds that can absorb these energies. And they can transfer energies to the chlorophylls, and so we can capture lots of energy, which is what we need to do. Now, if you capture energy, every capture does not actually cause an electron to flow. Okay? You can have a chlorophyll just sitting there. It absorbs light. It goes from the ground state, where the electron is in one of the orbitals, and it gets up into the other orbital, and it's in the excited state. The electron can transition back down, and it can give off energy, which is called fluorescence. Some things do fluoresce. This doesn't do us any good. Okay? Sometimes the energy, where it becomes excited, can go back down and transfer the energy to another chlorophyll. This doesn't help us out either in terms of actually moving an electron, but it does move the energy from one to another. And so energy can move around. If there is a special pair, though, the energy might be captured here, transferred from one, transferred to what's called the special center. Once the absorption occurs, and once the electron is excited, it can jump from one entity to another. That's where the electron starts to flow. This is where we can get the energy from. Within the cell, represented here, do you see these little hops? What we have is a network, a network of lots of different organic molecules that it can absorb light energy. Most of these do not actually allow an electron to flow. Most of them capture. They are antennas, and they transfer electrons and energies around until it gets to the special center. And so here are one chlorophyll that can be excited, a second chlorophyll that can be excited, and then the special center. So I get excited. Ooh, it's got lots of energy. And then it excites its neighbor. Ooh, that has lots of energy. And then it excites its neighbor. Ooh, it excites it, but do you see what happens here? It's organized a little bit different. It excites it, and this electron pair gets close to a second electron. Ooh, and electrons love to pair together, and so it gets close enough so that you actually allow the electron to move from one entity to the other, and you cause a positive-negative charge. You separate the charge. That's where the particular electron flow begins. And so that electron now is able to move from one entity to the other and flow down a pathway. The special center now has been excited, has given off its electron. All right? What is the energy necessary for a metal to lose an electron called? Way back in chapter something, GChem 1. The energy necessary to extract an electron. What? Okay, the energy given off when an electron accepted is called electron affinity. That's the opposite. When you lose an electron, you make an atom become a ion, and the energy is, what is it? Ionization energy. Okay, so effectively, the wavelength is optimized to make the ionization energy of the chlorophyll throw off the electron. All right? That chlorophyll is dead. Why? What do you think about ionization energies? First one you might be able to take off. How much energy do you need to take the second electron out of a system? Is it more or less? Why is it more? Why would something not want to lose its second electron? I hear somebody saying something. I don't see who's saying it. Okay. Let's say magnesium. That's what we're working with. It had 12 protons and 12 electrons, right? One of the electrons flew away because the light kicked it off. right? It now has 11 electrons and 12 protons. What happens to those 11 electrons now that are there? They are what? Yeah, they're attracted to the nucleus. Even better, right? Because it's now 12 pluses holding 11 minuses. It would take a lot more energy for us to take off another electron. Not enough for the light to do that anymore. So for us to actually do this again, we would have to give an electron back to chlorophyll before it can go again. And so we're going to excite chlorophyll, allow electron to leave, and then we'll have to give an electron back to chlorophyll for it to be able to go again. And we're going to have a lot of electrons flow for this whole process to proceed. Now, there are two different photosystems in photosynthesis. The photosystems are very similar to the complexes in oxidative phosphorylation, in which we had 4 of those. Here we only have 2. So at least we have less. Photosystem 1 will be optimized to use about a wavelength of about 700 nanometers, okay? And it leads, for the electrons to start flow, it leads to the synthesis of NADPH, and it leads to a pH gradient, which allows the synthesis of ATP. Photosystem II, on the other hand, uses a wavelength that is optimal around 680 nanometers. It leads to the synthesis of oxygen. It also gives me a pH gradient, which allows the synthesis of ATP. And so obviously we're going to start with photosystem, which? 2. Yes, why? I have no idea. Okay. Photosystem 2. All right. The players are the special pair of chlorophylls that we just talked about, which is called P680 because it has the maximal absorbance at 680. We're going to have some other players called pheophytin. I'll show you what that looks like. Plastoquinone, the cytochrome BF complex, and a protein called plastocyanin. These are carriers. Pheophytin is a chlorophene ring without the metal. It can absorb light, it can carry an electron, but it can't give an electron because it doesn't have extra electrons to give, but it can accept it, hold on for a second, and then pass it on. The plastoquinone is very similar, and we actually use the same nomenclature for Q, and we used Q before. I think the difference between the Q that we have in mammals and the Q that we have in plants is this moiety. I believe it is a ester, a methyl ester in ours, where this is just the methyl groups. But exactly the same. We talk about them as Q going to QH2. Plastocyanin is very similar to the protein cytochrome C in that most of the electrons are flowing through the membranes until it gets to a protein that is water soluble and it can move within the water from one place to another. In this case, it carries the electron in a copper, and so it changes between a +1 and a +2 state, and so it's going to carry the electron from the interior of the hydrophobic into the water portion between the two photosystems. All right, here is a picture of photosystem 2. We started talking about chlorophyll, so we started right here. And we know light is going to absorb, and it's going to excite lots and lots of different chlorophylls until it gets to this special center. And then it's going to kick off one electron, and it will kick off it from the chlorophyll to the pheophytin. All right. Now, I talked about one UV ray making one electron, but there are 4 in this slide. Why in the world does this slide have 4? Okay. It's all the stoichiometry. When we follow the stoichiometry from glycolysis, we did it all from 1 glucose. That was kind of the standard, and we counted everything from there. When we talked about oxidative phosphorylation, we talked about it in terms of 2 electrons because both FAD, H2, and NADH carry 2 electrons, so we carried it all the stoichiometry from 2. Here, quite often, what we're going to count the stoichiometry from is the production of 1 oxygen. So to produce 1 oxygen, we're going to have 4 electrons extracted from the water to produce the oxygen. So that's why we're getting a stoichiometry of 4. And so, but we have to do it 4 times to get this done. So I first take an electron and I excite it. I give it to pheophytin. Pheophytin will give it to 1Q that is bound and doesn't diffuse into the membrane. It then will give its electron to an iron center. The iron center will give it to a Q, which is called QB, which is actually able to migrate within the membrane system. And as long as it's picked up 2 of these, it will carry them to the cytochrome BF complex. Okay? The problem is, I excited one with light. I gave it, and I've only got 1 electron here. It can't leave. So I can't excite this until I reset it. I do that by taking an electron that is on, what does this represent? What is that? It's called, it's the amino acid tyrosine. It's a tyrosine radical. Okay? The tyrosine is actually holding an extra electron in the radical state. Once this reacts and becomes positive, it'll give up its electron to reset this so it can be excited again. Well, now this has a deficit of an electron. It's going to take it from this group right here called the OEC. Okay? This is the oxygen evolving complex. Okay? It's kind of an interesting complex. It is a group of manganese atoms that actually can extract the electrons from oxygen to create a whole bunch of electrons in that complex ready to feed to chlorophyll every time it gets excited. It will produce the oxygen. Okay, we do have some crystal structures that actually show these entities. They aren't full crystal structures, but we do have partial crystal structures to understand what's going on. So, 680 is that special center. The pheophytin and the QA are important in the first steps of this. Now, I'm going to say this is quick. All right, now, but I'll give you some definitions. The UV is absorbed. This gets excited. It will transition its electron into the excited state and give it to pheophytin. The P680 becomes positive because it lost an electron. The pheophytin now has a negative charge. It happens in less than 10. What does P stand for? Pico or picoseconds. How big is a picosecond? Yeah, it's 10 to the negative 12. It's not something that we normally even pull out. You know, we get down to milligrams, right? Even maybe micrograms. Nanograms is pretty small. Okay, we're talking picograms. Okay, so less than 10 picoseconds, that actually occurs. And then the transition of that electron from the pheophytin to the QA happens in 100 picoseconds. So this is a very, very quick transition. I'm actually surprised that they can actually even measure these timescales because that is quick. And it gives the electron eventually to Q. And it just sits there, and QA gives it to QB, and QB will catch its electron, be a negative with a radical, and just sit there. This really looks very similar to what we saw in complex 3, where 1Q just sat there with 1 electron, couldn't go anywhere for a while until a second one happens. We will then need to excite the P60 again, give it to pheophytin, give it to QA, give it to QB. At that moment in time, QB can actually start floating away and build up QH2 in the cytosol. Right here, there's supposed to be a tyrosine that gives its electrons back, and then the manganese center here, which is the oxygen evolving complex, that is going to reset these. Now, what is actually going to help us as this transition occurs, as the Q brings the electrons through, it's going to pick up protons from one side of the membrane. It will bring the electrons to the cytochrome BF complex, and it will give off the electrons on the inside. We're actually going to physically move, protons from one side to the next as electrons are moved across. Okay, the cytochrome BF complex, as it goes through its whole process, as it gives electrons through, the protons are actually moved from one side to the other. And what it will do is it will give its electrons to the protein plastocyanin. So it will diffuse, and I will have my electron now sitting inside the membrane. And plastocyanin is ready to reset P700 when it gets excited. And so at the end of Photosystem II, the electrons are in plastocyanin. All right, the oxygen evolving complex, let's take a look at that just a little bit more in detail. It is a complex of 4 manganese, a calcium, and a chloride, and within this there are 5 different oxidation states in which it can accept 4 electrons, and it can hold 4 full electrons ready to be transferred. So it can react with the oxygen, the water, produce oxygen, and create enough electrons to help fund the excitation of Photosystem II. All right? Every time that Photosystem II, the P680, is excited, becomes a positive state, the tyrosine radical gives its electrons to it. And do you see where the tyrosine radical is right here? It'll give its electrons to the P680. It'll take an electron from this group. And so it just hops over and hops over from one entity to the next until we get 4 excitations to create 1 oxygen molecule. To look at it another way, remember I said that every time electrons move from one entity to the next, it has to go down an electron gradient. That is without the addition of extra energy. We've also talked about the excited state. And so here's the P680. The P680 will absorb a photon. It will actually absorb energy, and this is the only time that it goes up the energy state because of that absorption of that UV energy. When the electrons go from the P680 to the pheophyton, it goes down the energy gradient. I lose a little bit of the energy right there. That could have been used to make ATP. The pheophyton will give it to the QA will give it to the QB, the QB will give it to the cytochrome BF complex, and I'll actually pump protons across the membrane, and then the cytochrome BF complex gives it to the protein plastocyanin. Again, each one of those moves down the energy gradient. Now, I will actually take electrons from water, put them into the complex, and I will gain electrons. I'll gain electrons to use. I'll gain the oxygen that's being produced. It'll give its electrons to the tyrosine radical. The tyrosine radical will be able to refund an electron into the P680 plus to bring it back to the ground state of P680 to be reabsorbed. And so the orientation of all of these, remember the P680 has to be in a very specialized, symmetrical positioning, and so that's what gives its ability to do this. The pheophyton is right next to it. The tyrosine is right next to that. The manganese is a complex. So they are all very close to each other so that no single movement of electrons is very far. All right, the end process of the Photosystem II. We actually have 4 electrons transferred through P680. we have 12 protons that are created as a gradient, or actually moved from one compartment to the next, and I produce one oxygen atom. Photosystem I is very similar in that I excite one electron at a time, and for every excitation of the P700, I will then reset with a plastocyanin the electron in that metal center. I'll go through a few players in the photosystem I. This one's kind of, it's a dimer, so if you kind of cut it right down the middle, that's kind of halfway through. P700 will give its electrons to chlorophyll. It will give its electrons to another chlorophyll. It'll give its electrons to a phyloquinone, a Q. It gives its electrons to some iron centers. And eventually, it will give its electrons, to a protein called ferredoxin. Ferredoxin is going to be a really important player. It carries electrons, and it is, again, like cytochrome C, it can carry its electrons in a water environment. The ferredoxin will take its electrons to an enzyme that is very important, ferredoxin NADPH reductase, and it will take two NADPH pluses plus two protons to make NADPH, two of them. The reason why we make two is that each one is a 2-electron carrier, and I have to move 4 electrons to make sure that the stoichiometry creates one oxygen. Each time I have an excitation of the P700, the plastocyanin has to give back an electron so it can be excited again. I will have to have a total of 4 plastocyanins to work through this, and I will have to have a total of 4 ferredoxins to allow this whole process to occur. Okay. Right here is a buildup of energy. And this energy is going to be used for synthetic processes. I'm going to make our carbohydrates from that. In this process of photosystem I had no protons move across the membrane so that I can make ATP. I just allow the NADPH to be made as the end product of energy. Okay, so we have a special pair at 700. I allow lots of separation. I allow things to move from place to place to place. I end up in ferredoxin. Ferredoxin goes to the reductase, and the reductase makes NADPH. If I show that in this type of slide, and I know you have a different one, but it has the same information. P700 gets excited. I go down all the different carriers until I get to ferredoxin. Ferredoxin then gives its electrons to the reductase, and I make my 2 NADPHs. All right. Ferredoxin is a water-soluble protein. Plastoquinone is a water-soluble protein. Everything else in the photosystems is within the membrane, whether it be Q or within the protein that is embedded in the membrane. All right. Hint. Okay. This might be important. This is the overall flow. 4 protons will hit photosystem II. The 4 photons, the reason why we use 4 is because we're producing 1 oxygen molecule. In that, water will be converted into oxygen. All right. I will also produce 4 protons. Photosystem has all of these electrons flowing around, gives it to the Q. Q brings them to the cytochrome BF complex. Okay, as part of the cytochrome BF complex, it allows 8 protons to be pumped from one entity to the next, from one compartment to the next. Okay, from what's called the stroma to the thylakoid lumen. The electrons from cytochrome BF complex go into plastocyanin. I have to have 4 of those. Photosystem 1 gets excited 4 times by 4 photons. I reset each time with plastocyanin. I give electrons to ferredoxin 1 at a time, 4 of them. And I go to the reductase. The reductase will accept 2 electrons, react 1 NADP plus, okay, and create NADP-PH. And I will then take 2 of them and create the second one. All right. As I do that, in actuality, I don't know, I think this is an error they had. 2 protons react with the NADPH to create the NADP plus to create the NADPH. All right, that is the overall flow of photons and electrons. Okay, I want you to make some corrections on your slide in your notes. The book I took this from had the stoichiometry to make half an oxygen. It's really hard to make half an oxygen, so we're going to change the values. Here's 1, oxygen. I have to produce 4 protons. To do that, I have 4 photons of light. I will take 8 protons and through the cytochrome BF complex, move the 8 into the membrane, the lumen. I'll take 4 plastocyanins. I will take 4 light absorptions, move them through. I will use 4 ferredoxins to go to the reductase, and I will take 2 NADPH pluses and 2 protons to create 2 NADPHs. Okay, same general outline as what we saw before. But there are a couple other things I want to identify in this particular piece. All right. There are 3 places that create a gradient. Okay. Is it 3? 1, 2, 3. Yeah, 3 places that create a gradient. Work with your partner and identify which 3 places create the gradient. Remember, a gradient is this. What I want is a concentration of protons that is big. Then I want an itty-bitty concentration here. Okay, so this is low and this is high. All right, anybody want to identify one place? One of the 3 that creates the gradient. The 8 protons actually being pumped across. That is done by the cytochrome BF complex. That is one of them. Where's the second? ATP synthase is going to break the gradient. We're not there yet. That's our next step. Where else is gradient formed?
Is there a gradient formed when the water becomes oxygen?
Yes. I do not move anything across a membrane, but I make more inside than outside. Okay. Last one. NAD plus. The reductase also helps create the gradient by doing this. makes the outside lower because it takes a couple of those protons and matches them into NADPH. Okay, so I have created the gradient in all three ways. I've created some on the inside. That creates more on the inside. I have pumped some from the outside to the inside. That definitely makes a gradient. And I've reduced how many free protons are on the outside. So I've used all three strategies to do that. All right? You have to have some physical protons to move through the synthase for synthesis to happen. But you also have to have a great enough change between the membranes for them to actually want to flow. Okay? And so I produce 12 that can be used for synthesis. All right. How many protons were needed in oxidative phosphorylation to make 1 ATP? 4, we said. 3 through the synthase, right? And then what? The oddball one. To transport the PI into the right place for synthesis to occur. All right, look at where the ATP synthesis is happening inside photosynthesis. How many total protons do I need to make ATP? Only 3, because the place where the synthesis of ATP happens and where the PI and ADP are in the same compartment. I don't have to move them from one place to another. I actually had to use energy in the body to make sure they were in the right compartment. Here, I don't have to use that extra energy. So it's a little bit more efficient because of the orientation. So how many ATPs can you make when you make 1 oxygen? 12 divided by 3 is 4. Good. And you would need 4 of these and 4 of those. So you can make 4 ATPs when you make 1 oxygen through this pathway. And the fact that I don't have to move any of the ADP or PI allows us to use the proton gradient a little bit more efficiently than in oxidative phosphorylation. So this is a compare-contrast issue between the two. Question or a stretch? Okay, question. So I have created 4 protons there and 8 protons there to make 12 protons that can go through the membrane. And at 3 at a time, I can do that 4 times. Even though these 2 up here do create a gradient, a differential, they can't be used to make ATP, but we have to have a certain concentration difference before that even starts. And that helps that concentration difference. All right. Now, here's a problem that I need a solution to. I can have light going, I can have light going, I can have light going. That's great. I have the whole system working, and then all of a sudden, if you have a lot of light, you can run out of that. That becomes a limiting reagent. You just don't have any NAD+. Okay? The plants have a system which can allow you to create more ATP even in the absence of NADP+ being available. Okay? It does it this way. This ferredoxin, which is going to have lots of important uses, when it builds up in concentration, it has the ability to go this direction, which can cause a little circle like this to happen. And so I can excite P700, I can make the electrons flow, I can get it to ferredoxin. Ferredoxin can bring it back to cytochrome BF complex. Cytochrome BF complex will pump protons across, and the plastocyanin will go back and reset P700, and I can have that cycle go, go, and go. I will make no more NADPH, but I can still make more proton gradient, and more proton gradient can make more ATP. Okay? If you take a look really closely, right here, you can see that same line called cyclic phosphorylation right there. Okay? And so I have the ability to continue to make ATP as long as there's light. Okay? The reason why I would run out of NADPH is I've got to use NADPH to do synthesis, and sometimes there's so much light, I actually am faster in moving electrons than I am in synthesizing sugar. And so I can make lots of ATP. Okay? Now, the proton gradient formation and the reason that light actually creates this can be simulated in the laboratory. And so we can take, in the dark, this organelle and place it into a pH, a beaker pH 4, and allow it to equilibrate. And so both sides are 4. And then I can throw it into a buffering system that now has a pH of 8, where inside is a pH of 4, which is high concentration on the inside, low concentration on the outside of protons, and lo and behold, it will start making ATP. Light doesn't have to exist for them to make ATP. All that it has to have is a difference in pH, a difference in proton gradient. So I can force it to go that way. I can create it experimentally. It's just, in nature, light is what makes that proton gradient actually occur. This is what needs to happen before any synthesis occurs. You need to have a pH differential, or a gradient, that is 3.5 units large. Okay? Give me a real number. 3.5 units, pH units. Give me a real number, what that means. What does 3.5 mean? Meaning that how big is the gradient between the top and the bottom, or the inside and the out? I know we use pH all the time, but do we actually even know what that means in real life? Yeah, negative log of the constant. That is perfect. That is a textbook answer. But what does that mean fundamentally? Okay? All right, let's do this. A pH difference of 1 between the inside and outside. Okay, it's a log based, right? So that means on the inside, it's 10 times greater than the outside. That would be 1. What would be a difference of 2? 1 on the outside, how much would be on the inside? 100. Okay. What's a pH difference of 3? 1 on the outside and 1,000 on the inside. What would be 4? 10,000. So what would be 3.5? Between 1,000 and 10,000, 5,000. It's about a 5,000 concentration difference between the inside and the outside. That's how much protons I have to pump across that membrane or make that differential before it actually starts working. Okay? And so that's what those pH values really mean. I have to have 5,000 more protons on the inside than the out. All right. Sometimes we want to kill plants. And so you can use a weed whacker or you can use a herbicide. And lots of herbicides have been made. Most of the time, herbicides are molecules that will involve disrupting this electron flow. And so the small molecule here, DCMU, actually blocks or gets in the same site that QB binds to. And so I can excite P680, I can give it to the QA, I can give it to that iron, and I can not give it to QB because this molecule is sitting in the way. What happens? I can't make ATP. I can't make NADPH. I can't make anything, and it withers and it dies. Okay? I can't. And you have another toxin that I show here gets in the transition in the P and the between the P700 and its transition to ferredoxin. This molecule was used in the war against drugs. They would spray it over fields of marijuana, and the marijuana would start to die. Well, businessmen got really mad about that, and so they started harvesting it very, very quickly and drying it out before it totally died. Unfortunately, what happened was they would dry it and that molecule would still be in the marijuana. And then people would package it in different ways and they would partake of it in ways that, you know, they usually do. And unfortunately, when it is burned, when you smoke, it produces toxins. And so not only were people getting high, they were also dying, which I guess on the war on drugs was not a bad thing from one particular perspective, but we stopped using that due to deaths. But what we do is use organic molecules to disrupt the electron flows with the use of herbicides. All right, not so great. The second part of photosynthesis is making sugar. And so what we will do is we will take all of that NADPH we just synthesized and all of that ATP we just synthesized, and we will create sugar. The most common sugar that is synthesized is what? Glucose itself. And then glucose is synthesized in mainly polymers, storage polymers. One of those is cellulose. The other is starch. Okay, cellulose is probably the single largest biomolecule that is synthesized in nature. And then, every so often, we make things called sucrose, which we enjoy and are important for us. Now, both nutritionally, starch and sucrose are wonderful for us. Cellulose, not so much, although we do need a little bit of roughage in our diet, and so cellulose provides that. But most of these molecules come from plants themselves, and it will come eventually from the CO2 that at some point in time somebody breathed out. It will be taken in by the plant cell and synthesized back into sugars. And so we'll talk about the fixation of CO2 or carbohydrate synthesis next time that we come together.